we are going to start the course Nanotechnology in Chemical Engineering. Today we will discuss about material characterization techniques XRD. So, in our previous class already we have discussed various characterization techniques. So, today the X-ray diffraction techniques, that basically will discuss basic components and working principles, determinations of average crystallite size, that is from the X-ray diffraction patterns, and then a few examples considering various metal oxides or nanoparticles that we will consider, and then that we will discuss. So, from the X-ray diffractions, the equipment, so this techniques means X-ray diffractions which is called XRD. So, this is very effective method for the determinations of the crystallite structure or crystal structure of the materials. So, the materials will prepare that may be in the form of bulk forms, crystallite forms or nanoforms. So, once we characterize with the help of X-ray diffraction patterns or X-ray diffraction study, so then we can say that the materials may be either it is in amorphous forms or in maybe crystalline forms. So, when that materials we can see it is amorphous materials, its atoms that is present in that particular materials, that would be not orderly arranged, that is randomly distributed in that particular material. So, then we can say the materials is amorphous materials. When the atoms are orderly arranged in a specific pattern, so then we can say that materials is crystalline materials. So, that crystalline materials may be single crystals or maybe a polycrystals depending upon that materials preparations or synthesis. So, from X-ray diffraction patterns, so once we get a specific patterns for a particular material, so once we analyze, so then we can say that whether the material is amorphous or crystalline at that specific temperature or conditions we have maintained to prepare that material. So, once it is the material is amorphous, so then I said that atoms will be randomly distributed. So, there is no specific order of arrangement. So, therefore, the patterns will get there is no sharp peak. So, as a result broad that would be present in the XRD patterns in case of amorphous materials. So, in case of the crystalline materials, when that materials forms a crystalline structure, so then the atoms would be arranged in a orderly arrangement should be there, the atoms, and therefore the periodic and repeating patterns will get, and the X-ray diffraction patterns will get, that would gives a sharp diffraction specs of that particular metals, metal oxides or the materials is present in that particular material. So, we can easily see the materials having a sharp peaks we can get from that X-ray diffraction pattern. So, in X-ray diffractions, what are the materials present, that is crystalline. So, they are different, means the materials having crystalline structure. So, we can describe the crystal structures in different way, means cubics or tetragonals, orthorhombic, rhombohedral, hexagonal, monoclinic or triclinic. Different way we can describe the crystal systems that is present in that crystalline material. So, that already have discussed in our previous lectures also. So, here you can see means the atoms, that is I said when it is amorphous materials, they are the atoms that would be distributed randomly, and in case of the crystalline materials, so you can see the atomic arrangements is orderly. So, then by this way you can say that materials is whether it is amorphous materials or the crystalline materials. So, here you can see the means just example of scheme is showing. So, how we can get from particles to different polycrystalline materials, and from one crystals to single crystal. So, here this is single crystals materials, and here you can see this is a polycrystalline material. So, in that material different type of arrangement or more than one crystals present. So, in that particular grain, so then we can say that materials whether it is single crystalline, polycrystallines or maybe amorphous, depending upon the method of synthesis we can classify the materials whether it is amorphous or crystallines or it is single crystals or maybe a polycrystalline material. So, in X-ray diffraction patterns I said there are different crystal systems is present, 7 crystal systems when the materials is crystalline. So, these are the different systems which are present, that is theoretical study. So, once we get a particular diffraction patterns and the materials we get X-ray diffraction patterns, so we can analyze based on the data. So, we can say that specific type of arrangements is there. So, in that also when despacing is also important when we study the X-ray diffraction patterns. So, despacing, Miller indices, these are the components are very important. So, with the X-ray diffraction patterns with the help of means the patterns, so we can get that particulars, means a crystals forms different type of planes. So, the planes that is represented by this type of integer 3 integer HKLs. So already have discussed in previous class also. So that is basically the intercept of the planes with the crystallographic axis. So in the X-ray diffractions equipments, how does it work? So in equipment, so there is X-ray tube, that is the source of X-ray. One detector is there. So once X-ray source monochromatic X-ray will fall over the sample, so it would be diffracted. So diffracted X-ray that would be collected in the detectors or detect, and based on that, so you can get X-ray diffractions patterns. Okay. So here means once we get from that detector the signals or that samples or materials we have placed over there. So here so we can see that this is the intensity y axis and x axis to theta, or that angle. So that is we can see here's this angles to theta. So samples and detectors, in between that angles, that is the 2 theta. With that, I mean, so once samples will rotate, the tubes and detectors remains fixed, samples will rotate. So then the X-ray diffractions patterns will get, and this it would looks like this. Okay, so for a specific materials it is showing. So depending upon the materials we have prepared, the nanomaterials or bulk materials we have, so depending upon that different type of patterns will get. Okay, so that we have to analyze depending upon the materials, its crystal structures, or it is amorphous phase, which type of specific metal oxides is present in that, we can detect with the help of X-ray diffractions patterns. So here I said that X-ray diffractometer, so that is operate. So two different way it can be operate. So first one is the 2 theta arrangement. So here X-ray tubes is there and this is the detectors. So these two remain fixed, and most of the cases X-ray diffractometers, so this is these two remains fixed, and only samples that would be the rotates from a specific angle to higher angle. So with the step size, specific step size is there, with that gradually move and X-ray diffractions patterns will be collected. Okay, so and another one is the theta arrangement. So theta, that is in case of the samples and detectors, these samples and detectors remain fixed, only X-ray tubes that will be rotates at specific angles or step size is there. So that way also it can be, means that X-ray diffractometers may operate. Okay. So here different type of materials I am showing. So different type of X-ray diffractions patterns we can get. So in case of the gas, liquid, solid samples or nanocrystalline samples, so depending upon the material, so the diffractions patterns will be different. So here in case of the gases, so it don't produce any distinct diffractions patterns like solids or nanomaterials we have, so or amorphous. So in case of the liquids, it exhibits a forms of diffractions that is due to the less distinct than solids due to their short range of order. So in case of the liquid, so when that is we have solid materials, so it produced a distinct set characteristics diffractions patterns. So from there we can get different crystallite structures or crystalline planes, so we can get from the X-ray diffractions patterns. And when case of nanocrystallines, so that is smaller than conventional crystalline materials, so it gives a unique diffractions patterns that influenced by the size and arrangements of that atoms present in that particular nanocrystals. So here, so with the help of the X-ray diffractions patterns or X-ray diffractions XRD patterns, so whatever the will get, so with that we can get various type of informations here. Phase identifications, materials, it may be pure materials is present or maybe different metal oxides metals is present, mixed metal phases are present, so that we can identify. Or also we can, means I said that whether the materials is crystallines or amorphous, so depending upon degree of crystallinity, that we can evaluate with the help of this X-ray diffractions techniques. Also crystallite size we can measure. So when that may be materials amorphous phase or maybe crystalline phase, so if that materials is amorphous phase, that peak broadening will be there. So and in case of the crystallines crystallinity is there, so then say particular crystallite size of that materials we can get with the help of this X-ray diffraction patterns. Also we can find out the lattice strains and defects also. I mean sometimes peak shifting is there, means when suppose a pure materials we have, with that if some impurity or other materials contaminations is there, so that is called some defects. So as a result, some peak shiftings also is possible to observe. So with the X-ray diffraction patterns, once we are analyze that, okay. Even phase identifications, that is also possible. So I said the peaks are matched with the standard reference patterns that is exist. So that is called JCPDS or ICDD database is there. So whatever the new materials or materials we have, so we get a particular specific X-ray diffraction patterns, and standard database is there. So we can compare and we can match with our samples. So then we can say what particular type of metals, metal oxides or phases are present in that particular materials that we have. So here for example, so in case of TiO2 materials, so there are anatase or rutile phase, so that we can see by considering the X-ray diffraction patterns of that particular metal oxide TiO2. So different peak positions we can get with the X-ray diffraction patterns, and we can analyze that. Okay. So next is the determinations of average crystallite size. So mostly we want to calculate, once we have the X-ray diffraction patterns, is particular specific planes of that particular crystalline materials we get from the X-ray diffraction patterns. So once we know that's X-ray diffraction patterns, so then we can find out the crystallite size, that is the average crystallite size we can estimate. So here's this equation is called Serre equations. Using we can find out the L, that is the crystallite size. So here K is the equations constant. So here usually we take 0.9, lambda, that is the wavelength of the X-ray that is used, that usually 0.154 nanometers, that depends upon that X-ray wavelength that is being used for that specific X-ray diffractometer. And then beta, that is the full width half max, so that we can get from that X-ray diffraction pattern that we can use, and theta is that specific Bragg angle. So that is the from that X-ray diffraction means patterns we can get, and that can be used to calculate the average crystallite size. Here you can see, so here's a particular peak at particular positions to theta value was taken. So here's full width half max, that this is the total length, and this is the full width half max at full width. So here's this we can find out, that is actually beta. So full width at half max, so this is the half max, that particular position. So we can measure this particular distance, and then we can that is in terms of degree, and then we can convert that into radians, and that you have to use here's this beta, and cos theta value is here, 2 theta value we can get, and then divided by 2 we will get theta, and then k and lambda value that is given, and then crystallite size we can calculate. So that will show. Okay. So here's in the X-ray diffractometer, that is actually works based on the principles of the Bragg's law. So here's Bragg's law is n lambda equals to 2d sin theta. So here's n is the integer, x is the lambda is the X-ray wavelength, and this is the spacing between two different planes. So here's this is plane 1, plane 2. So in between that distance, that is called this spacings actually. So it is the Bragg's angle, so that we can get from that X-ray diffractometer. So here's theta is the Bragg's angles. Okay. So I said there are seven crystal systems are present in the crystalline material. So that may be cubic, tetragonals, orthorhombics, rhombohedrals, hexagonals, monoclinic or triclinic. So that depends upon their lattice parameters, that is the distance means ABC, and corresponding angles also in this alpha, beta and gamma, and corresponding length also, depending upon that the particular class of crystals that would be forms. Okay. So depending upon that, so it would be different. So here's Miller indices already I have discussed. So here's let's say a axis length, that ABC, that is the, let's say for one example. So here we can get 4 to 1s a, this is particular planes. So these planes having 4 to 1 notations Miller indices, and another planes, this is another planes, it has 0 and 0. So how that is coming from the, if we know that axis length is 4, 8 and 3, and intercept length that is 1, 4 and 3, then fractions of intercept that would be 1 divided by 4, so that is 1/4, and this is 4 by 8, that is 1/2, and 3 by 3, that is 1. So that is the fractions intercepts for this particular planes we can get, and then inverse of these fractions intercepts will get 4, 2 and 1. So that would be the HKL value. So that is actually specifically this planes indicates actually 4 to 1, so that specific plane. Similarly 0 1 0, so that planes also we can get, that is the Miller index, that locations of that particular planes in that particular materials that is present. So we can get with the help of this axis length and intercept lengths. By using that, so we can get Miller indices. Okay. So then spacing between atomic planes of the crystals, so that is the d value that we can also get by using these equations, also Bragg's equations, or using, let's say, for a cubical crystal systems is there. So if you know the lattice parameters and each scale value, and then d spacings we can calculate by using these equations. So here for a cubic systems, crystal systems, similarly for other systems also we can find out the d spacings in between two different planes we can calculate if you know the lattice parameters and Miller indices of that particular crystals, that is planes present in that particular materials. So here few examples we can show, so then it would be clear. So means suppose we have prepared, see here's one materials, that is Bismuth scandium oxide, lead titanium oxide. So that materials was taken and that materials was prepared at 500 degrees centigrade. So that temperature was maintained 500 degrees centigrade, but here means when that material was calcined or prepared, so that was calcined at different times, 0 hour to 70 hours. So initially it was the materials this. So when 0 means at the beginning, we can 0 hours this materials is like this, and then if we wait for 3 hours, so then slightly crystallinity means crystals growth is present there, and then if we increase, there you can see the materials gradually converted amorphous to the crystalline phase at the same temperature by waiting longer period of time. So times of activations or calcinations when we prepare a material, so that is very important. So means if we change or increase the time of calcinations, then materials maybe initially it was amorphous phase, gradually it would be converted into crystalline phase, and crystallite size you can see gradually increase. So initially it was very small or dispersed or maybe amorphous phase, so then 13 nanometers, 17, 24 nanometers, that way. So that materials gradually agglomerated and crystallite size of that specific crystals of this particular sites that gradually increase. So from the collecting the X-ray diffraction patterns, we can analyze the changes of that crystallinity of that materials we can see. So similarly another examples is showing, so here titania, that material was taken and that materials was calcined at different temperatures. So here initially before calcinations that materials was taken and the X-ray diffraction patterns, so that small peak was observed, and once we increase the calcination temperature from low temperature to gradually high temperature, so up to that peak maintains this particular phase. So after 500, so from 600 onwards you can see, so these particular phase intensity gradually increase and this particular phase gradually decrease. So this particular phase actually rutile phase of TiO2, and this is anatase phase of the TiO2. So at low temperatures when it was remain that samples calcined at low temperatures, this particular anatase phase was dominated. Okay. And there was no formations or changes of the phase of rutiles was observed at low temperature when gradually increase the calcination temperature at high temperature. So then anatase phase gradually converted into rutile phase or other phase conversions that easily we can see. So this type of means phase changes in that materials by once we prepare that materials at different calcination temperature we can observe. So with the help of X-ray diffraction patterns we can analyze and that materials whatever we have prepared, so how effective for a specific applications we can easily see. So now here's Fe2O3, that materials that was prepared at different method of synthesis. So same materials we can prepare by a number of methods are available. So here this particular materials Fe2O3 ferric oxide that was prepared by 6 different methods. Material compositions is same, the irons and oxygens is present, but here you can see that depending upon the method of synthesis, so a particular specific peak if we consider, So intensity of that particular peak is different from one materials to another. So here it is strong peak observed, so of Ap2O3 material. So strong peak, it indicates the materials is highly crystalline. And so hence if we see into this method third, so here there is no peak present, means peak is broadened, so there is no peak, it indicates, or peak broadening it indicates the materials is amorphous state, means here the materials that is prepares Ap2O3 that using this particular method, so the materials or means Ap2O3 that remains highly amorphous or smaller crystallines or a smaller amorphous phase. So deep same materials, if we prepares low temperatures or that specific method, so we can get or synthesize that materials is amorphous phase, and using these methods we can get this iron oxide, but that is crystalline phase. So depending upon our applications, we can prepare that materials by using a specific phase, and we can get a specific property that may be useful for that particular applications. Similarly, another examples I am showing. So here's crystallite size determinations already have discussed. So here's, let's say, this particular peaks we are getting, so that peak positions you can see to theta value, that is approximate 36 to theta value. So theta would be 18. So this is 36 to theta locations, and fully max, that beta value that was measured manually, here this is value, and that it is coming approximate 0.26 degrees. So that we have converted into radians, and then k and lambda value we know, and theta value we know. So theta, beta, k, lambda value we are putting, and then we can get crystallite size of this particular peak, we can get 30 nanometers. So by that way we can, using Serre equations, we can calculate the crystallite size of that particular planes or particular peaks that is present in that particular materials. Okay. Also another example, so where crystal structures we can see. So here CDS was taken and X-ray diffraction patterns was obtained. So in this pattern, so you can see 100, 002 or 101, three different planes are present in that particular CDS crystals, and here it was later obtained that depending upon these crystal planes, so Urchite crystal structures specific, this is theoretical study. So we can say that one, that material CDS was prepared, and this type of crystal structure is present in that particular materials whatever we have prepared. Okay. So another example is nanoparticles. So initially, let's say the materials we have prepared, so that may be larger size, bulk size, that is 1 micron. So if we means change the materials by means microns to nanometer range, so here you can see that this particular peak gradually when that materials was larger crystallite size, so then this peak was more intense, and once gradually changes from 1 micrometer to 50 nanometer, 25, 15, then gradually lowers our dimensions, means materials we converted into the nano size. So then the peak gradually sharp peak to the peak broadenings we can observe. So okay, strong peak to the means peaks, here is no peaks present, so in this particular positions or locations. So that we can say that, so when larger particles too are converted this CDS into smaller crystallines, so then gradually that would be smaller rods means dispersed in that particulars, or very small particles formations is there. So here inside you can see that when 5 nanometer to 1 nanometers it is converted, so these peaks gradually disappear. So it is bump like means X-ray diffraction patterns we are getting, or peak broadenings that is observed. Okay. So initially it was sharp peaks and then gradually peak broadening. So another examples, particle size distribution and morphology on X-ray diffraction patterns. So here's 5 nanometers CDS powder that was taken and X-ray diffraction pattern was obtained, and another 25 nanometers crystallized size of that CDS powders that was prepared, and then both were mixed, means 75% 5 nanometers of CDS and 25% of 25 nanometer CDS, both were mixed, homogeneous mix combined, and then we have done the X-ray diffraction pattern. So here we can see, so for these smaller nanometers, 5 nanometers, when that materials was prepared 5 nanometer size, so it was broadening, and when it was 25 nanometer crystallized size, so then it was sharp. So in the mixtures also similar, so means presence of two different size, means one is smaller, another one is larger crystallite size. So both the materials present at different size. So you can see with the help of X-ray diffraction patterns, we can say that there is some two different combinations of the materials is present, or different mixtures is present. So depending upon their X-ray diffraction patterns. Another example is there. Here the effect of nanoparticle shapes on X-ray peaks, that is also very important. So here three different type of materials or shape was taken or prepared. Here is spherical, rectangles, and here cylindrical shape of same materials. Three different shape was given. So then X-ray diffractions was collected for these particular materials. So here you can see the peak intensity, means here this peak, particular specific peak intensity when the materials was spherical in shape. So here's peak intensity we can observe. So when it is cubical shape, so then intensity little bit decrease. When it is cylindrical shape, so then its intensity we can see sharp peak we can observe. So this type of means depending upon different shape also, means particles we prepared, if it is different shapes, so same compositions may be same, but different shapes, means the particles you have prepared, nanomaterials or nanoparticles. So depending upon their shapes also, patterns also will change. Okay. So thank you. So today is up to this.